Imagine you're building a house, right? You pour the concrete foundation, you lay down all the bricks, you paint the walls.
Sounds like a lot of work.
Right. And eventually you walk inside and it looks beautiful. Like the architecture is stunning. But, and here's the catch, when you try to turn on the lights, nothing happens.
Oh, no.
Yeah. The doors are literally glued shut. The faucets don't work. The whole house is basically just this beautiful, completely frozen monument.
That's exactly what the modern web looks like without interactivity. It's entirely static.
Exactly. So today we are finally wiring the house for electricity and plumbing. We're doing a deep dive into Chapter 8 of your iTech 1030 web programming course, which is all about JavaScript and CSS animations.
Yeah, this is where it gets really fun.
It is. The mission for this deep dive is to, extract the actual mechanics of how you move from that flat, static page to a fully dynamic client-side experience. It's like, I don't know, it's like learning the magic spells that finally bring Frankenstein's monster to life.
I like that analogy. But to understand how we actually wire that house, we first have to talk about where this new code is. Well, where it's actually running.
Right. The location matters.
Huge shift here.
Yeah.
The source material for this chapter draws a really hard line between what you learned in Chapter 7 with PHP and what you're learning now with JavaScript.
Okay, let's break that down.
So PHP is a server-side language. You can think of it as a factory that's like miles away from the house.
Okay.
That factory builds the HTML, it packages it up, ships it across the internet, and then, this is the key, its job is completely done.
So PHP decides what HTML to send, but once that package actually lands in your browser, the connection back to the factory is totally severed.
Exactly. If the user clicks a button, PHP has no idea. It cannot see it.
The server is basically blind to what's happening on the screen. So to react to the user, we need a language that runs natively inside the browser itself, on the user's actual device.
Right, and that is JavaScript.
It wakes up the exact moment the HTML lands on the screen.
Yeah, and for JavaScript to actually do anything meaningful, it needs a way to store data right there in the local memory of the browser. Which brings us to variables.
Right. The slide deck introduces variables. Specifically, it talks about let and const. The basic concept is that you use let when you declare a variable whose value is going to change later, and const for a value that's set once.
Simple enough.
But what stands out immediately to me is the total absence of the old var keyword. Like, it's just gone.
Oh, yeah. var is pretty much dead in modern development. The old var keyword had this incredibly unpredictable behavior regarding scope-like, where a variable could actually be accessed in your code.
It was messy, bro.
Super messy.
Yeah.
It would often just leak out of its intended container and cause these really hard-to-track bugs.
I hate those.
Right. So modern JavaScript defaults to const to enforce strict predictability. You lock a value in place, and if some other part of your code tries to accidentally overwrite it, the browser throws a hard error instead of just quietly failing.
Which is actually helpful.
It saves you hours of debugging. You only intentionally drop down to let if you're writing a variable that inherently must change.
Like a user's score in a web game, right? Going from 0 to 10.
Exactly. Perfect example.
Okay, let's unpack this const thing, though, because I was looking really closely at the slides, and there's something that feels like a massive contradiction to me.
Uh-oh. What is it?
Well, the text clearly states that const cannot be reassigned. But right beneath that, it explicitly says that if your const is holding an array or an object, that array or object can still be mutated.
Oh, right.
If it's a constant, how is it mutating? It feels like it breaks its own rule.
Yeah, honestly, this trips up almost every single developer the first time they see it. But it makes perfect sense once you look at how the computer's memory actually operates.
Okay, I'm listening.
When you declare a const, you are not locking down the data itself. You are locking down the specific memory address that the variable name points to. Think of const as locking a heavy safe to the floor.
Oh, I see. So you cannot pick up the safe and swap it out for a completely different safe.
Exactly. The container is bolted down. The variable name will always point to that exact safe. But, and here's the trick, the door to the safe is still unlocked.
Wait, really?
Yeah. You can reach inside and add new items to the array or take properties out of the object. The safe itself hasn't moved, so the rule of const hasn't been violated.
Oh, wow. Okay. So locking the container prevents you from accidentally overwriting the entire structure, but you can still manage the data inside of it dynamically.
Exactly. It's just a much safer way to write code.
So we have a secure way to store users' data using constant let. But data just sitting in a safe isn't doing anything.
Nope, just gathering dust.
Right. The browser needs a set of instructions on what to actually do with that data when, say, the user submits a form. That brings us to functions. A function just wraps a block of code so you can write it once and execute it as many times as you need.
Yeah, they're the workhorses of JavaScript.
The source shows the classic declaration syntax, using the actual word function, and then the newer arrow syntax, which uses an equal sign and a greater than sign to point to the code.
Yeah, both syntaxes tell the JavaScript engine to package a set of instructions into a reusable block. The classic declaration is highly readable when you have, like, a complex operation spanning 20 lines of code.
Makes sense.
But the arrow syntax strips away all those boilerplate words, making it ideal for really tiny single-line operations.
And inside those functions, we use logic like if and else statements to make decisions, or loops like for each to iterate over arrays.
Which is great, but
But how does that abstract logic actually touch the visual elements on the page? Like, how does JavaScript know where a specific heading or an image is actually located?
okay. This is where it gets real. It uses the document object model, or the DOM.
The DOM.
Yeah. When the browser receives the raw HTML text from the server, it doesn't just, blindly paint the text on the screen. It runs that text through an internal parser and constructs a live in-memory tree of nodes.
Okay, a tree.
Every single paragraph tag, every div, every image is converted into an individual object. And JavaScript is basically designed to interface directly with this tree.
Oh, I get it. It's like the raw HTML is the original 2D blueprint of the house.
Right.
But the DOM is a live 3D architectural model sitting on a table. If we want to change something, JavaScript first has to locate that specific piece of the model.
That is exactly it. And the slide deck introduces a method called querySelector to do just that.
And you just feed it the exact same CSS selectors you already know, right?
Yep. So document.querySelector H1 just tells the browser's engine to scan that DOM tree and return the first heading object it finds.
What if I want all of them? Say I have 20 product cards on a page.
Then you'd use querySelectorAll, which hands you back a collection of all those objects so you can loop through them.
But finding the element is only the first step. The real magic is altering it.
Yet the DOM provides specific properties attached to these objects. For instance, if you want to swap an image, you just access the setAttribute method on the image object.
And then what? The picture just changes.
Well, when you change the SRC attribute, the browser immediately notices the DOM has updated, fires off a network request to fetch the new image, and repaints that section of the screen dynamically.
Just like that. That's so cool. Now, the source material makes a really clear distinction between two ways to change the text inside an element: text content and inner HTML.
Oh, yeah. This is a big one.
If I have a specific chair in my 3D architectural model, using text content feels like reaching into the model and just instantly painting that chair blue. It only affects the visible surface. But inner HTML seems, I don't know, fundamentally different.
It's very different. Text content is a direct, completely harmless update to the text node in the DOM. The browser treats whatever you pass into it strictly as letters and numbers,
Okay.
but inner HTML is much heavier. When you pass a string to inner HTML, you are commanding the browser to wake up its whole HTML parser again.
Oh, really?
Yeah, takes the string, reads it for HTML tags, literally tears down the existing branch of the DOM tree, and constructs entirely new nodes based on what you provided.
Wow, so it's rebuilding the furniture, not just painting it.
Exactly.
And the slide deck explicitly warns us to use inner HTML carefully, especially with user input. Let me see if I have this right. If I build a comment section and a malicious user types actual JavaScript code wrapped in HTML script tags,
Yep, I know where this is going.
and I inject their comment using inner HTML, the browser's parser will wake up, read those script tags, and just execute their code directly on the computers of everyone visiting the site.
Yes. That is known as a cross-site scripting vulnerability, or XSS. It's one of the most common security flaws in the web.
That is terrifying.
It really is. By forming the habit of defaulting to text content, you strip the browser of its ability to parse tags.
So it just shows up as text.
Exactly. If a user types malicious code, text content ensures it just prints out on the screen as harmless, visible characters. You only use inner HTML when you specifically need to generate new structural elements from scratch.
Okay, noted. So we can find elements, and we can securely update their content. But the browser needs to know when to execute these functions.
Right.
If the JavaScript runs the millisecond the page loads, the user hasn't even had time to move their mouse yet. We need triggers.
Which the browser handles through something called an event loop. It constantly monitors the hardware, the mouse, the keyboard, the screen for any interactions.
Like a guard dog.
Yeah, and when an interaction occurs, it broadcasts an event. As a developer, you use add event listener to tell JavaScript to sit and wait for a specific broadcast and only run your function when it hears it.
The source highlights some pretty incredible events beyond just basic clicking. There is the input event. Instead of waiting for a user to hit a submit button, input fires every single time the state of a form field changes.
Every single time.
If you press a single key, it fires. If you paste text, it fires.
Yeah, the slide deck uses the input event to demonstrate a live character counter. Think about the user experience of typing a password, and there's that small counter below telling you in real time exactly how many characters you've typed.
I love those.
They're great. Under the hood, the browser is just listening to the keyboard buffer. Every time the buffer updates, the input event triggers a tiny JavaScript function. That function reads the length property of the text field and then uses text content to update a number on the screen.
So fast. There is also an event called DOM content loaded. The notes explain that this fires when the initial HTML document has been completely loaded and parsed into the DOM tree without waiting for heavy assets like images or CSS to finish downloading.
Right.
But why not just wait for the whole page to finish loading?
Well, if you try to run JavaScript that selects an H1 element, but the browser's parser hasn't actually reached the H1 in the HTML document yet, your script will just fail.
Oh, because it's looking for a node that doesn't exist in memory yet.
Exactly. Wrapping your initial setup code in a DOM content loaded event listener guarantees that the 3D model of your house is fully built before your JavaScript walks in and starts trying to move the furniture.
That makes perfect sense. Now, the slide deck shows another really practical example. The auto-updating copyright year.
Oh, Clyde.
We've all seen the copyright symbol and the year in the footer of a website. The source shows how to use JavaScript's built-in date object, specifically calling newDate.getFullYear, to grab the current year from the user's operating system and then inject it into the footer span.
Yep, very common trick.
But frankly, I have to ask, why go through the trouble of writing a JavaScript function for something as basic as a 4-digit year? Why not just type 2025 in your HTML file?
I get that. But think about the administrative overhead of a large corporate website. If you hard code the year in the HTML footer, a developer has to remember to log into the server, open the file, manually change the text, and deploy the site every single December 31st.
And people forget.
All the time. And if they forget, and a customer scrolls down in February and sees a copyright of 2022, it signals that the website is abandoned.
It totally erodes consumer trust.
Exactly. Because JavaScript executes client-side,
Right.
it just asks the browser's internal clock what year it is at the exact moment the page loads. It runs silently, requires zero server maintenance, and guarantees the date is always accurate.
It's a tiny automation, but it solves a massive human error problem.
Huge. So we have the logic driving the data, but raw data instantly snapping into place feels, well, jarring. A premium web experience relies on motion to guide the user's eye and provide feedback.
Which is where we transition into the second half of the chapter, CSS animations.
Yes. JavaScript calculates the logic, but CSS handling the actual rendering of the movement.
The first tool introduced is the transition property. Like, we use CSS states like .hover to change a button from light blue to dark blue. Without a transition, the color swaps in 1 millisecond.
It's aggressive.
Yeah, but the transition property smooths that swap over a defined period. The syntax just asks for the property to change, the duration, and the timing function. For example, transition, background color 0.3s ease in out.
And that timing function dictates the mathematical curve of the animation. Like, a linear timing function moves at a constant robotic speed.
Which looks weird.
Right, because physical objects in the real world don't move that way. They have mass, they take time to accelerate, and they decelerate before stopping. Ease in out mimics that physics curve, making the interface feel grounded and natural to the human eye.
Okay, here's where it gets really interesting to me, the transform property.
Oh, transform's the best.
This lets us manipulate an element's appearance without affecting the surrounding document flow. We can scale it up, rotate it, or use translate Y to physically slide it up or down the screen. I kind of think of the transform property like a visual hologram of the element.
The hologram?
Yeah. If I use CSS margins to push a block of text down, every single paragraph below it gets shoved out of the way.
Right. The whole page stutters.
But if I use translate Y to move the element, I'm just moving the hologram. As far as the browser's layout engine is concerned, the original element hasn't moved an inch, so nothing else on the page gets displaced.
That hologram metaphor maps directly to how browser rendering engines handle performance, actually. When you change a margin or a width, you trigger what is called a reflow.
A reflow.
Yeah, the browser's CPU has to recalculate the physical geometry of the entire DOM tree, every node. That requires massive processing power. But when you use transform, the browser pulls that specific element onto its own hardware-accelerated layer, often handing the math directly to the device's GPU.
Oh, wow. So it shifts the pixels without recalculating the page geometry.
Exactly, which explains why the slide deck explicitly warns us about using the keyword all in our transitions.
Right. The notes say that all is a shortcut but targets every property, so we must be specific when performance matters.
Because if you command the browser to transition all, the engine has to actively monitor the geometry, color, and layout of the element on every single frame.
That sounds exhausting for the computer.
It is. By explicitly declaring transform point threes, you tell the browser it only needs to monitor that GPU accelerated layer. This is how you achieve buttery smooth animations at 60 frames per second, especially on, older mobile devices.
So transition is perfect for simple state changes, like hovering over a button. But the source also covers at keyframes for complex multi-step animations.
Yeah, at keyframes are for when you need real control.
You give the animation a name, and then you map out its behavior using percentages. At 0%, you set the starting styles. At 100%, you set the ending styles.
And you can inject entirely different styles at 25 or 50% to create like bouncing or pulsing effects. Then you just apply it to an element using the animation property, defining the duration and how many times it should iterate.
The slide deck features a really specific technique using at keyframes to create an animated gradient background. Have you seen this?
Yeah, it's a very popular aesthetic right now.
You apply a multicolored background gradient to the page body, but you set the background size to 200% by 200%, basically stretching the wallpaper so that it is twice as large as the wall itself.
So half of the colors are hidden entirely off screen.
Exactly. Then you use a keyframes loop to slowly shift the background position property from one corner to the opposite corner over, say, 10 seconds. I saw this in the deck, and honestly, my first thought was that constantly recalculating a giant gradient on an infinite loop must completely drain a user's laptop battery.
It's a fair concern. If you were doing this by having JavaScript recalculate every pixel frame by frame, it absolutely would destroy the battery.
But it doesn't.
No, because you're using CSS background position. The browser's rendering engine heavily optimizes the process. It rasterizes the oversized gradient image just once, and then simply slides that static image back and forth across the viewport.
Oh, that is so clever.
Right. You get a complex, flowing visual effect for almost zero processing cost.
And for you listening, you will actually be building this. For assignment 1, you are provided starter con, and you get to choose 3 out of 6 complex CSS animations to build, and that gradient technique is one of the options.
Highly recommend trying that one.
Yeah, it looks great. But this brings us to the bridge. We have JavaScript managing the data and the events. We have CSS optimized to handle the rendering of motion. How do we connect them? Like, how does JavaScript actually trigger the at keyframes animation?
The architectural philosophy here is separation of concerns. CSS defines what the animation looks like. JavaScript decides when it runs.
Okay.
You do not want JavaScript writing raw CSS. Instead, you define an animated state in your style sheet under a specific class name, like .box.visible, and attach your at keyframes to that class.
And then in your JavaScript, you listen for a click event, and you use the classlist.toggle method to attach or remove that .visible class from the DOM node.
Exactly. By simply toggling a string of text in the class attribute, the browser instantly applies the CSS rules associated with that class, and the animation begins.
But wait, if JavaScript is so powerful, why not just write the animations entirely in JS using the .style property we talked about earlier?
Because it creates a tangled mess.
Yeah.
This keeps your JavaScript files focused purely on user logic, and your CSS files focused purely on visuals.
Separation of concerns.
Right. When you tackle assignment 2, where you must add 3 JavaScript functions and 1 CSS animation to your final capstone site, the temptation will definitely be to write the animation logic directly in JavaScript because you have that power.
Don't do it.
You must resist that urge.
Right.
Rely on the classlist.toggle bridge. It ensures your code remains modular, performant, and incredibly easy to debug.
It really seems like a dynamic web page is a tag team effort across the entire stack.
Absolutely.
PHP builds the initial structural foundation on the server. The DOM parses that structure into a live interactive map in the browser's memory. CSS utilizes hardware acceleration to create smooth, performant motion. And JavaScript acts as the nervous system, listening to the user's input and toggling the classes that trigger the action.
Beautifully summarized. And, think about the broader implications of this client-side power.
Where are we going with this?
Well, the source material teases Chapter 9 next, which covers SQL and PHP database connectivity.
Right.
If JavaScript can handle all the user interaction, calculate logic, and completely rewrite the structure of the DOM without ever refreshing the page, what exactly is the server doing after the initial load?
Wow, that completely flips the dynamic.
It does. As you move into database connectivity, start looking at the browser not as a static document viewer, but as an independent software application running natively on the user's machine.
So the server isn't the factory building every page anymore.
No, the server becomes a quiet librarian sitting in a back room. The JavaScript application in the browser just sends a quick message asking the librarian for specific raw data, and then the browser decides how to render it.
That is such a powerful way to look at it. Well, we have wired the house. The electricity is on. Make sure you apply these concepts, practically dive into assignment 1 to experiment with the animations, integrate them into your capstone for assignment 2, and test your understanding of the mechanics on the 25-question quiz. Have fun making the web actually move, and we will catch you on the next deep dive.